Welcome to this coding problem walkthrough. In this session, we'll tackle LeetCode problem number 666, path sum 4. This is an interesting problem where we compute the sum of all path sums in a binary tree represented in a special format. Let's dive in and explore how to solve it efficiently. In this problem, we are working with a binary tree that is represented in a unique format using a list of integers. Each integer in the list has 3 digits. The first digit, or the hundreds place, tells us the depth of the node in the tree, starting from 1 at the root. The second digit, or the tens place, specifies the position of the node within that depth, also starting from 1 and moving left to right. Finally, the third digit, or the ones place, represents the value of that node. Importantly, this structure ensures that the tree is always a valid binary tree. For any node, its left and right children, if they exist, will be found in the next depth level. Specifically, the left child will be located at position 2 position 1, and the right child will be at position 2 position. Our goal is to calculate the total sum of all root-to-leaf paths in this tree. A root-to-leaf path is simply the sequence of node values along a path from the root node down to any leaf node, and its sum is the sum of those values. The output for this problem is a single integer representing the total sum of all root-to-leaf path sums. Let's explore an example to make this clearer. Suppose the input is nums equals 113, 215, 221. Here, the tree structure can be visualized as having a root node with a value of 3, and 2 child nodes, a left child with a value of 5, and a right child with a value of 1. This is derived from the input format, where 113 represents a root node at depth 1, position 1, with a value of 3, 215 represents a node at depth 2, position 1, with a value of 5, and 221 represents a node at depth 2, position 2, with a value of 1. With this structure in mind, we can now calculate the sum of all root-to-leaf paths. In this example, there are 2 root-to-leaf paths. The first path is from the root node with value 3 to the left child with value 5. Adding these together gives a sum of 8 for this path. The second path goes from the root node with value 3 to the right child with value 1, resulting in a path sum of 4. Adding these 2 path sums together, we get the total path sum for the tree, which is 8 plus 4 is equal to 12. This is the output for the given input. Now let's consider another example to further solidify our understanding. If the input is nums equals 113, 221, the tree structure changes slightly. Here, the root is still a node with value 3, but there is only one child node, located to the left, with a value of 1. This is because the input only specifies these 2 nodes. In this case, there is only one root-to-leaf path, which is 3-1. Adding the values along this path, we get a sum of 3 plus 1 is equal to 4. Since there is only one path, the total path sum is simply 4. Let's look at a final example with a slightly larger tree to understand how the calculation scales. Consider the input nums equals 111, 217, 221, 315, 325. Here, the root node has a value of 1, with 2 child nodes, a left child with value 7 and a right child with value 1. Additionally, the left child of the root has 2 children of its own, both with a value of 5. This creates 3 distinct root-to-leaf paths. The first path is 1-7-5, which sums to 1 plus 7 plus 5 is equal to 13. The second path is identical to the first, also summing to 13. The third path is from the root to the right child, 1-1, which sums to 1 plus 1 is equal to 2. Adding these together, the total path sum for the tree is 13 plus 2 is equal to 40. This shows how the problem can be extended to more complex trees while still following the same principles. Finally, let's review some constraints and edge cases to keep in mind while solving this problem. To tackle the path sum 4 problem, we need to calculate the sum of all root-to-leaf path sums in a binary tree. What makes this problem unique is how the tree is represented. Each node is given as a 3-digit integer, where the hundreds digit indicates the depth of the node, the tens digit specifies its position within that depth, and the ones digit gives the node's value. Using this encoding, we can identify each node's position and value in the tree. The challenge is to compute the total of all path sums efficiently. Let's discuss the potential strategies we can use to solve this problem. One straightforward way to approach this problem is the brute force method, where we explicitly construct the tree and then compute the path sums. First, we parse the input to extract the depth, position, and value of each node. Using this information, we build the tree in memory, typically using a dictionary to map each node's position to its value. Once the tree is constructed, we perform a depth-first search (DFS) traversal. During the traversal, we keep track of the current path sum and add it to the result whenever we reach a leaf node. While this approach is conceptually simple, it has some drawbacks. Specifically, building the tree adds unnecessary overhead, as we can solve the problem without an explicit tree structure. Although its time complexity of O(n) is reasonable, the space required for storing the tree adds inefficiency. A more efficient solution is the optimized approach, which avoids explicit tree construction altogether. Here, we leverage the structure of the input encoding to compute the path sums directly. The key insight is understanding the parent-child relationship. A node at depth d in position p will have children at depth d plus 1 in positions 2p1, left child, and 2p, right child. By storing the node values in a dictionary with keys as depth, position, tuples, we can infer these relationships directly. Using this representation, we can traverse the tree using DFS or BFS, maintaining a running sum for the current path. When we reach a node with no children, we add the current path sum to the result. This approach processes each node exactly once, achieving O(n) time complexity, and uses O(n) space for the dictionary, making it both time and space efficient. The optimized approach is the preferred solution here because it eliminates the overhead of building the tree while still capturing the structure of the problem. By leveraging the encoded input to deduce parent-child relationships, it achieves efficiency without sacrificing clarity. This strategy processes the input in linear time and uses linear space, which is optimal for this problem. Additionally, it avoids unnecessary complexity by working directly with the input rather than constructing an intermediate representation. However, it does require careful bookkeeping to ensure correct traversal, as it relies solely on the encoded format. This trade-off is worthwhile because the optimized approach strikes a good balance between simplicity, efficiency, and scalability, making it ideal for larger inputs and a clear choice for solving path sum 4 effectively. In this problem, we're tasked with computing the sum of all path sums in a binary tree represented in a special encoding format. Each node is defined by a 3-digit integer. The hundreds digit indicates the depth of the node, the tens digit specifies the position within that depth, and the units digit represents the value of the node. Our objective is to find the total sum of all root-to-leaf paths. To solve this, we'll use a dictionary to store the tree structure where keys are tuples of depth and position, and values are the node values. Additionally, a queue will help us traverse the tree level by level using breadth-first search, enabling us to compute path sums efficiently. These data structures ensure that we process each node just once and avoid redundant computations. The algorithm can be broken down into key steps, starting with parsing the input and building the tree representation. The first step is to parse the input list and construct a dictionary representation of the tree. Each node in the input is converted into a key-value pair where the key is a tuple of depth and position, derived from the first 2 digits, and the value is the node value, derived from the last digit. For example, given the input, 113, 215, 221, we build the dictionary as follows. The root node at depth 1, position 1, has a value of 3, the left child at depth 2, position 1, has a value of 5, and the right child at depth 2, position 2, has a value of 1. This structure allows us to quickly access any node and its children. Next, we initialize the BFS queue. Each element in the queue is a tuple of the node's key and the current path sum. Starting with the root node, we initialize the queue as 1, 1, tree, 1, 1. This setup ensures that we can traverse the tree while keeping track of the cumulative path sums. Now we perform the BFS traversal. While the queue is not empty, we dequeue the front element, which includes the current node and the running sum of values from the root to this node. For each node, we calculate the keys for its potential children. The left child is at depth plus 1, position *2 to 1, and the right child is at depth plus 1, position *2. If either child exists in the dictionary, we add it to the queue with the updated path sum by including the child's value. If neither child exists, we know the current node is a leaf, and we add the current path sum to the total sum. This process continues until all nodes have been processed. This approach ensures that we only visit each node once, and we efficiently compute the total path sum by keeping track of the running totals. Once the BFS traversal is complete, we return the total sum of all root-to-leaf path sums. The algorithm is designed to handle edge cases effectively. For instance, if the tree contains only one node, the total sum is simply the value of that node. If some nodes are missing at certain levels, the dictionary inherently handles this by not including those nodes. In terms of complexity, the time complexity is O(n), where n is the number of nodes, as we visit each node exactly once during the BFS traversal. The space complexity is also O(n), accounting for the dictionary storage and the queue used during traversal. This makes the solution both time and space efficient, even for larger trees. Finally, we translate this logic into a Python implementation for clarity and execution. The Python implementation begins by building the dictionary representation of the tree. Each node in the input list is processed to extract its depth, position, and value, which are then stored in the dictionary. Next, we initialize a BFS queue with the root node and its value, and we define a variable total_sum to accumulate the sums of all root-to-leaf paths. Inside the BFS loop, we process each node by checking for its children. If a node has no children, it is a leaf, and its path sum is added to the total. If children exist, they are added to the queue with their respective path sums. This process continues until the queue is empty. Finally, the function returns total_sum, which represents the total of all root-to-leaf path sums. This implementation is both concise and robust, handling edge cases and ensuring efficient computation for any valid input. Here, we start by defining a class solution and the function pathSum that takes a list of integers, nums, as input. The first step is to build a dictionary called tree to store the value of each node, where the keys are tuples representing the node's depth and position, and the values are the node's numerical value. For each number in nums, we extract the depth, position, and value by decomposing the number using division and modulus operations. These are then stored in the tree dictionary. Next, we initialize a variable total_sum to 0, which will eventually hold the sum of all paths from the root to the leaf nodes. To compute these path sums, we define a helper function DFS that performs a depth-first search. This function takes three parameters: the current depth, the current position, and the cumulative sum of values along the current path. Inside the DFS function, the first check ensures that we proceed only if the current node exists in the tree dictionary. If the node exists, we add its value to current_sum, which keeps track of the running sum for the current path. Then, we calculate the positions of the left and right children of the current node. These are determined based on the current depth and position, with the left child positioned at depth +1, position *2 to 1, and the right child at depth +1, position *2. Finally, we need to determine whether the current node is a leaf node by checking if neither of its children exists in the tree dictionary. If the current node is a leaf node, meaning both its left and right children are absent in the tree, we add the current_sum to the total_sum and terminate the recursion for this branch. Otherwise, we recursively call the DFS function for both the left and right children. These recursive calls continue until all paths from the root to the leaf nodes have been explored. Once the DFS function is defined, we initiate the depth-first search by calling DFS with the root node, which is always at depth 1 and position 1, and starts with a cumulative sum of 0. Finally, after exploring all paths, the total_sum variable will contain the sum of all root-to-leaf paths, which we return as the result of the pathSum function. This implementation efficiently traverses the tree structure represented by the nums input, leveraging a dictionary and recursive DFS to compute the desired result. Here, we start by defining the class solution and the method pathSum, which takes an array of integers called nums as input. Each number in the array represents a node in a binary tree encoded as 3 digits. The first digit is the depth, the second digit is the position at that depth, and the last digit is the node's value. To organize this information, we use a hash map called tree, where the key is a string representing the depth and position of a node, and the value is the node's value. We populate this map by iterating through the nums array, extracting the depth, position, and value from each number. Next, an array totalSum is defined to store the cumulative sum of all root-to-leaf paths. Since we need to explore each path in the tree, we define a helper function dfs4 performing a depth-first search. This function will recursively traverse the tree, starting from the root node at depth 1 and position 1, and calculate the path sums. The pathSum method then returns the total sum once the traversal is complete. The DFS function begins by constructing a key for the current node using its depth and position. If the key does not exist in the tree map, this means the current node does not exist in the tree, so we simply return. Otherwise, we add the value of the current node to the cumulative sum, current sum. Then, we calculate the keys for the left and right children of the current node. A node is considered a leaf if both its left and right children are absent from the tree map. In this case, we add the current sum to total sum, 0, and return, as we've reached the end of this path. If the node is not a leaf, we recursively call DFS for both the left and right children, passing along the updated cumulative sum. This allows the function to explore all possible paths in the tree, ensuring that every root-to-leaf path is accounted for in the final total sum. To solve this problem, we first need to build the tree structure from the input array nums equals 113, 215, 221. Each number in the array is formatted as dppv, where d represents the depth of the node, pp is the position of the node at that depth, and v is the value of the node. For example, the number 113 corresponds to a node at depth 1, position 1, with a value of 3. Similarly, 215 corresponds to a node at depth 2, position 1, with a value of 5, and 221 corresponds to a node at depth 2, position 2, with a value of 1. Using this information, we construct a tree represented as a dictionary 1, 13, 2, 15, 2, 21. With the tree structure in place, we proceed with a depth-first search, DFS, traversal, starting from the root, 1, 1, with an initial current sum of 0. At the root, the value is 3, so we add it to the current sum, resulting in current sum equals 3. The root has two children, a left child, 2, 1, and a right child, 2, 2, and we will explore these paths one by one. First, we traverse to the left child, 2, 1, which has a value of 5. Adding this value to the current sum gives current sum equals 8. Since 2, 1 has no children, it is a leaf node, so we add this path sum of 8 to the total sum. After completing this branch, we backtrack to the root and now explore the right child, 2, 2, which has a value of 1. Adding this value to the current sum gives current sum equals 4. Similar to the previous path, 2, 2, is also a leaf node, so we add this path sum of 4 to the total sum. At this point, we have visited all paths in the tree, and the total sum of all root-to-leaf paths is total sum equals 8 plus 4 equals 12. We return 12 as the final output for this example. In this second example, the input nums is 113, 221. As before, we start by building the tree structure. The number 113 corresponds to a node at depth 1, position 1, with a value of 3, and 221 corresponds to a node at depth 2, position 2, with a value of 1. This gives us a tree represented as 1, 1, 3, 2, 2, 1. Next, we perform a DFS traversal starting from the root, 1, 1, with an initial current sum of 0. At the root, the value is 3, so current sum equals 3. The root has two potential children, a left child, 2, 1, and a right child, 2, 2. However, 2, 1, does not exist in the tree, so we move directly to 2, 2. At 2, 2, the value is 1. So adding this to the current sum gives current sum equals 4. Since 2, 2 has no children, it is a leaf node, and we add this path sum of 4 to the total sum. With no more paths to explore, the total sum of all root-to-leaf paths in this example is total sum equals 4. We return 4 as the final output. Now, let's look at a more complex example where the input is nums equals 111, 217, 221, 315, 331. First, we construct the tree. The number 111 corresponds to a node at depth 1, position 1, with a value of 1. Similarly, 217 corresponds to 217, 221 corresponds to 221, 315 corresponds to 315, and 331 corresponds to 331. The resulting tree structure is 1, 1, 1, 2, 1, 7, 2, 2 1 3 1 5 3 3 1. With the tree built, we initiate a DFS traversal from the root 1 1 with an initial current underscore sum of 0. At the root, the value is 1, so current underscore sum equals 1. The root has two children, a left child, 2 1, and a right child, 2 2. First, we explore the left child, 2 1, which has a value of 7. Adding this value gives current underscore sum equals 8. This node has two potential children, a left child, 3 1, and a right child, 3 2. We traverse to 3 1, which has a value of 5. Adding this value gives current underscore sum equals 13. Since 3 1 is a leaf node, we add this path sum of 13 to the total underscore sum. The right child, 3 2, does not exist, so we backtrack to 2 2. At 2 2, the value is 1, so current underscore sum equals 2. This node has two children, a left child, 3 3, and a right child, 3 4. We traverse to the left child, 3 3, which has a value of 1. Adding this value to the current sum gives current underscore sum equals 3. Since 3 3 is a leaf node, we add this path sum of 3 to the total underscore sum. The right child, 3 4, does not exist, so our traversal is complete. The total sum of all root to leaf paths in this example is total underscore sum equals 13 plus 3 equals 16. We return 16 as the final output. This concludes the walkthrough for all examples, demonstrating how we systematically parse the input, build the tree, and calculate the sum of all root to leaf paths using DFS. To analyze the time complexity of the algorithm, we start with the process of building the tree dictionary. For each number in the input array nums, the algorithm extracts the depth, position, and value of the node using simple integer operations. Since this extraction involves a constant amount of work per number, and there are n elements in nums, this step operates in n time. Then, we move to the depth-first search, or DFS, which traverses the virtual binary tree represented by our dictionary. In this traversal, every node is visited exactly once. The number of nodes, m, depends on the input and corresponds to the number of unique nodes specified by nums. In the worst case, where the input represents all nodes of a complete binary tree up to a maximum depth, the number of nodes is proportional to 2d1, where d is the depth. Thus, the DFS step operates in m time, making it efficient given the constraints of the problem. Now, combining these two steps, the overall time complexity of the algorithm is n plus m. Since the number of nodes in the tree, m, is directly proportional to the number of elements in the input array nums, we can simplify this to n. Next, let's consider the space complexity. The first contributing factor is the tree dictionary. This dictionary stores one entry for each node in the tree, and in the worst case, all n elements of nums correspond to unique nodes. Therefore, the space required for the dictionary is n. Another factor is the call stack used during the DFS traversal. Since the DFS uses recursion, the maximum depth of the recursion corresponds to the height of the tree, which depends on the maximum depth value in the input. In a balanced binary tree, the height is log m, but in the worst case of a skewed tree, it could be m. These two components together determine the total space usage of the algorithm. Taking both components into account, the overall space complexity is n plus h, where h represents the height of the tree. In the worst-case scenario of a skewed tree, the height h can be as large as n, leading to an overall space complexity of n. Comparing this to a brute force approach, a naive solution might involve explicitly generating all possible paths in the tree and summing them up. This approach would have an exponential time complexity of 2 to the power of d, in the worst case, where d is the maximum depth of the tree, and it would require significant memory to store all paths. However, the optimized solution avoids this inefficiency. By directly calculating the path sums during the DFS traversal and simulating the tree with a dictionary, the algorithm achieves a linear time complexity relative to the number of nodes. This makes the optimized approach far more efficient and scalable. Finally, we justify the big O complexity mathematically. The time complexity is n, because each node is visited exactly once during the DFS traversal, making the process linear with respect to the number of nodes. Additionally, constructing the dictionary requires a constant amount of work for each node, which scales linearly with n. For space complexity, O(n) is justified because the dictionary stores at most n nodes, and the recursive call stack depth is proportional to the tree height, which is bounded by n. Together, these factors ensure the algorithm is both time and space efficient, avoiding the exponential growth of a brute force approach. This efficiency makes the solution well suited for handling the constraints of the problem while maintaining a clean and optimized implementation. When solving this problem, there are several common mistakes to watch out for. First, misinterpreting the 3-digit encoding format is a frequent issue. Remember, the hundreds digit represents the depth of the node, the tens digit is the position within that depth, and the ones digit is the value of the node itself. Both the depth and position are 1 indexed, so if you treat the position as 0 indexed, you might assign nodes to the wrong parents. This brings us to the second common mistake, incorrect parent-child mapping. A node's position determines its parent, and you can calculate this using the formula parent_position equals position plus 1 / 2. If you don't apply this formula correctly, the tree structure will be inaccurate. Another area where mistakes happen is handling missing nodes. The input array might not include all possible positions at a given depth, so you need to account for these gaps when calculating path sums. Additionally, some solutions use inefficient traversal methods, like explicitly building the entire tree. This can waste both time and memory, so it's better to use a hash map to store node information and compute sums directly. Finally, overcomplicating the logic by using recursive traversal after tree construction can introduce unnecessary complexity and increase the chances of bugs. Simplifying your approach will often lead to a cleaner and more efficient solution. This problem is designed to test a range of skills, including your ability to interpret encoded data and efficiently simulate a tree structure. Rather than relying on brute force methods like full tree construction, interviewers are often looking for solutions that demonstrate a deeper understanding of optimization. Using a hash map is an excellent strategy here, as it allows for fast lookups to store and retrieve node information without needing to explicitly build the tree. It's also important to think about edge cases. For example, what happens if the input represents only a single node, if there are missing levels in the tree, or if the tree is unbalanced? Being prepared to handle these scenarios can set you apart. Additionally, if time permits during an interview, discuss potential optimizations such as avoiding unnecessary traversal or exploring iterative methods, as this shows a proactive approach to problem solving. To reinforce your understanding, you might also want to explore related problems. LeetCode 112, for instance, deals with finding a root-to-leaf path that equals a given sum, while LeetCode 113 extends this by asking for all such paths. LeetCode 129 focuses on summing root-to-leaf numbers, and LeetCode 437 challenges you to count paths that sum to a specific value. Practicing these can deepen your grasp of path sum problems. There are several alternative approaches you can consider for this problem, each with its own trade-offs. One efficient method is hash map-based traversal. Here, you store node values in a hash map, using the depth and position as keys. This allows you to compute path sums directly without explicitly constructing the tree, which saves memory. However, this approach requires careful indexing to ensure correctness. Another option is explicit tree construction, where you build the tree using a class to represent nodes and then traverse it to compute the sum. This method is often easier to implement conceptually, but it comes with the overhead of constructing the entire tree, which can be less efficient. Lastly, you can use iterative path summation, simulating the tree traversal with a stack or queue. This avoids recursion, which might be helpful in environments with limited stack size, but it can introduce more complexity in handling edge cases, such as missing or unbalanced nodes. Selecting the right approach depends on the constraints of the problem and the trade-offs you're willing to make between implementation complexity and performance. Great work on completing this problem. To summarize, we used a hash map to reconstruct the tree and a depth-first search to calculate the path sums. This problem highlights the importance of understanding tree structures and applying efficient algorithms like DFS. Thanks for watching, and stay tuned for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!